So this is the third week of the problem solving live sessions on soil mechanics geotechnical engineering 1. Previously the problem solving sessions were on the origin of soil, the soil classification, basic index properties, seepage diagrams. And today the topic is soil compaction, seepage and permeability. So like the last few sessions, this session will be combining of a set of questions followed by a discussion session on the solutions. And the questions will comprise of someone have joined, I see. The questions will comprise of MCQ, MSQ, there is the multiple select questions, some true false statements if it is there, and numericals. So I'll be starting with dictating all the questions at first. Those who are joining, they are requested to write down the questions or take a screenshot, whatever, of the questions. After that, I'll give you some time. On average, I'll give you 15 minutes of time to solve the questions. After that, after 15 minutes of break, I'll start my discussion. I'll start discussing the solutions of each and every problem in this session. Okay. So, good evening. I'll just start with the third live discussion session on soil compaction, seepage, and permeability. So, those who have joined, I'll repeat. I'll first dictate the questions. You are asked to write down all the questions or take a screenshot of them, whatever is comfortable with you. And then, after dictating all the questions, I will be giving you some time to solve the questions. Don't tell the answer while I'm dictating the question. I'll give you time to solve the questions, and then after that time I will again start the session. In the same session, the meeting will be on. I'll just start the session and I'll start discussing the solutions to each problem. Okay. So I hope the PPT is visible and I am audible. Mokshit Rajavardhan. Am I audible and the PPT is visible? Visible? Okay, fine. So I'll start dictating the questions now. Yes. So the first question here is factors affecting compaction of a soil are. Factors affecting compaction of a soil are. This is an MCQ. It is the multiple choice question. You need to answer. There is only one answer for this. The options are water content, soil type, compaction energy, or all of these. I'll repeat the question. Factors affecting compaction of a soil are. Your options are water content, soil type, compaction energy, or all of these. I hope you are familiar with the term water content and compaction energy. Compaction energy is the energy which is being produced while giving the compactive force, compactive effort during soil compaction. Okay. So, water content or soil type or compaction energy or all of these factors affecting soil compaction. I'll go to the next question. Yes. For a same soil type, the effect of heavier compaction is 2. For the same soil type, the effect of heavier compaction is 2. Now this is a multiple select question, MSQ, so more than one option might be correct. The options are: decrease the optimum water content, increase the maximum dry density, decrease the effective shear stress, increase the maximum dry density. So I'll just repeat the question. For the same soil type, the effect of heavier compaction is 2. The options are: decrease the optimum water content, decrease the maximum dry density, decrease the effective shear stress, or increase the maximum dry density. Okay, I hope the question was clear. I'll go to the next question. The water content used in field compaction is known as. The water content used in field compaction is known as. The options are: optimum water content, field water content, placement water content, or natural water content. I repeat the question. The water content used in field compaction is known as optimum water content, field water content, placement water content, or natural water content. Next question. The variables concerning the method used to compact a given soil include. This is again a multiple select question. The options are: manner of operation, weight of the equipment, area of contact, or time. Sorry. I'll repeat the question. The variables concerning the method used to compact a given soil include manner of operation, weight of the equipment, area of contact, time. Next question. The line showing dry density as a function of water content in the absence of air is called. Absence of air void is called. Just a second. Yes. The line showing dry density as a function of water content in the absence of air voids is called. The options are: zero saturation line, no air voids line, maximum compaction line, or saturation line. I'll repeat: the line showing dry density as a function of water content in the absence of air voids is called. Zero saturation line, no air void line, maximum compaction line or saturation line. Next question. In modified Proctor test, the soil is compacted in, the options are 2 layers, 3 layers, 4 layers or 5 layers. I'll repeat the question. In modified Proctor test, the soil is compacted in, the options are 2 layers, 3 layers, 4 layers or 5 layers. I'll go to the next question. A soil sample has specific gravity of 2.7 and optimum moisture content 16%. What is the theoretical maximum dry density in gram per cc that can be achieved for this soil? So this is a numerical. The options are 0.185, 1.896, 1.885, 1.785. Write down the data given very carefully. I'll repeat the question. A soil sample has specific gravity of 2.7 and optimum moisture content 16%. What is the theoretical maximum dry density in gram per cc that can be achieved for this soil? Your options are 0.185, 1.896, 1.885, 1.785. Next question. Again a numerical. Cohesive soil yields a maximum dry density of 1.8 gram per cc at an OMC, that is optimum moisture content of 16% during a standard Proctor test. The specific gravity of the soil is 2.65. From this determine part A, the void ratio of the soil, part B, the degree of saturation, and part C, the maximum dry density it can be further compacted to. I'll repeat the question. A cohesive soil yields a maximum dry density of 1.8 gram per cc at an optimum moisture content of 16% during a standard Proctor test. The specific gravity of the soil is 2.65. Determine the void ratio of the soil, the degree of saturation, and the maximum dry density it can be further compacted to. Okay, I'll go to the next question. Seepage velocity is. Seepage velocity is. The options are rate of discharge per unit cross section area of soil, rate of discharge per unit cross section area of voids, Discharge velocity under constant head or discharge velocity under variable head? I'll repeat the question. Seepage velocity is, that is, the definition of seepage velocity is rate of discharge per unit cross section area of soil, rate of discharge per unit cross section area of voids, discharge velocity under constant head or discharge velocity under variable head. Next question. A soil has a discharge velocity of 6 into 10 to the power minus 7 meter per second and a void ratio of 0.5. The seepage velocity in 10 to the power minus 7 meter per second is, the options are 12.18, 18.18, 12.62, 18.62. I'll repeat the question. A soil has a discharge velocity of 6 into 10 to the power minus 7 meter per second and a void ratio of 0.5. The seepage velocity in 10 to the power minus 7 meter per second is, the options are 12.18, 18.18, 12.62, 18.62. Next question. Flow between any two points in a soil depends on the difference between. Flow between any two points in a soil depends on the difference between. The options are pressure head, velocity head, datum head, or total head. I'll repeat the question. Flow between any two points in the soil depends on the difference between. The options are pressure head, velocity head, datum head, or total head. Next question. In a falling head permeability test on a silty clay sample, the following results were obtained. Sample length 12 cm, diameter 80 mm, initial head 1200 mm, final head 400 mm. Time for fall in head 6 minutes, standpipe diameter 4 mm. Find the coefficient of permeability in centimeter per second. All the options are in 10 to the power minus 5. The first one is 9.289, second one is 9.181, third one is 9.859, last one is 9.478. I'll repeat the question. In a falling head permeability test on a silty clay sample, the following results were obtained. Sample length 12 centimeter, diameter 80 millimeter, initial head 1200 millimeter, final head 400 millimeter, time for falling head 6 minutes, standpipe diameter 4 millimeter. Find the coefficient of permeability in centimeter per second. Next question. Permeability in stratified soil deposits show greater magnitude in direction. Permeability in stratified soil deposits show greater magnitude in direction. The options are parallel to stratification, perpendicular to stratification, inclined to stratification, or now these. I'll repeat the question. Permeability in stratified soil deposits show greater magnitude in direction. The options are parallel to stratification, option 2, perpendicular to stratification, option 3, inclined to stratification, option 4, none of these. Next question. What will be the ratio of average permeability in horizontal direction to that in the vertical direction for a soil deposit containing of consisting of three horizontal layers if the thickness and permeability of the second layer are twice of those of the first and those of the third layer twice those of second? It means there is a soil strata which has three horizontal layers. Now for thickness and permeability both, okay, the one in the first layer, the property in the first layer has been double in the second layer, and that in the second layer have been doubled in the third layer. Okay, so ratio of average permeability in horizontal direction to the vertical direction, this you have to find out. Okay, the options are 21 by 7, 3 by 7, 18 by 7, or 9 by 7. I'll repeat the question. What will be the ratio of average permeability in horizontal direction to that in the vertical direction for a soil deposit consisting of three horizontal layers if the thickness and permeability of the second layer are twice of those of the first and those of the third layer twice those of second? The options are 21 by 7, 3 by 7, 18 by 7, and 9 by 7. Okay. Okay, I'll go to the next question now. Calculate the coefficient of permeability in meter per day of a soil sample 6 centimeter in height and 50 centimeters square in cross-sectional area if a quantity of water equal to 430 ml passed down in 10 minutes under an effective constant head of 40 centimeter. So here the soil sample length or height is given 6 centimeter. The cross-sectional area is given 50 cm square. Now the value of discharge is given as 430 ml in 10 minutes. And during the discharge, the effective constant head was 40 centimeter. So now, what is the coefficient of permeability? That is the value of K. Okay. The options are 1.53, 1.65, 1.86, or 1.78. I'll repeat the question. Calculate the coefficient of permeability in meter per day of a soil sample 6 centimeter in height and 50 centimeter square in cross-sectional area if a quantity of water equal to 430 ml passed down in 10 minutes under an effective constant head of 40 centimeter. The options are 1.53, 1.65, 1.86, or 1.78. Next question. The line within a dam section below which there is positive hydrostatic pressure. The line within a dam section below which there is positive hydrostatic pressure. The options are cutoff line, phreatic line, flow line, or pressure line. I'll repeat the question. The line within a dam section below which there is positive hydrostatic pressure. The options are cutoff line, phreatic line, flow line, or pressure line. Okay. Next question. Soil at the toe of a dam has void ratio 0.62 and G, that is the specific gravity of soil solids, is 2.62. Assuming factor of safety of 5, the permissible exit gradient is. Options are 1, 0.5, 1.05, or 0.2. I'll repeat the question. Soil at the toe of a dam has a void ratio 0.62 and G equal to 2.62. Assuming factor of safety of 5, the permissible exit gradient is. The options are 1, 0.5, 1.05 or 0.2. Okay. Next question. This is again a multiple select questions. Yes. So more than one option can be correct. The question is elevation of a point with respect to any arbitrary datum is called. Elevation of a point with respect to any arbitrary datum is called. The options are pressure head, position head, total head or elevation head. I'll repeat the question. Elevation of a point with respect to any arbitrary datum is called pressure head, position head, total head or elevation head. Okay. So next question. In a flow net, there are 4 flow paths and 15 equipotential drops. If the head loss is 3 meter and K equals to 2 into 10 to the power minus 5 meter per second, estimate the quantity of seepage in meter cube per second. So there are 4 flow paths and 15 drops. The head loss is 3 meter and K is given as 2 into 10 to the power minus 5 meter per second. What is the quantity of seepage loss in meter cube per second? So the first option is 4.2 10 to the power minus 5, then 2.2 10 to the power minus 5, then 1.6 10 to the power minus 5, and then 4.2 10 to the power minus 4. I'll repeat the question. In a flow net, there are 4 flow paths and 15 equipotential drops. If the head loss is 3 meter and K equals to 2 into 10 to the power minus 5 meter per second, estimate the quantity of seepage in meter cube per second. Okay. Next question. Seepage pressure is option 1 equal to pore pressure, option 2 impact pressure of precipitation on soil, option 3 pressure exerted by percolating water on the soil, option 4 none of these. So what is the definition of seepage pressure? I'll repeat once. Seepage pressure is equal to pore pressure, impact pressure of precipitation on soil, pressure exerted by percolating water on soil, or none of these. Okay. Next question. A homogeneous earth dam is 52-meter high with 2-meter freeboard having 25 equipotential drops and 4 flow channels. If the coefficient of permeability is 3 into 10 to the power minus 3 centimeter per second, calculate the discharge in meter cube per second per meter length. So again a numerical. The dam has a height of 52 meter with 2 meter freeboard. There are 25 equipotential drops and 4 flow channels. Given K equals to this one, what is the rate of flow or discharge? Your options are 0.00036, 0.00024, 0.0036 or 0.0024. I'll repeat the question. A homogeneous earth dam is 52 meter high with 2 meter freeboard, having 25 equipotential drops and 4 flow channels. If the coefficient of permeability is 3 in 10 to the power minus 3 centimeter per second, calculate the discharge in meter cube per second per meter length. The options are 0.00036, 0.00024, 0.0036 or 0.0024. Okay. Sir, how to check my answer is right or wrong? I will discuss the answer, okay? There are few more questions left. Then I'll give you some time to solve these questions. After 15 minutes, I'll again join this meeting. I'll be in the meeting. You also stay in the meeting. After 15 minutes, I'll again start the class and discuss all the answers, okay? So even if you can't answer, don't worry. I'll discuss the answers with you. Okay. So this is the question. I'll go to the next one. Yes. Portion between two adjacent equipotential lines and adjacent flow lines is called. Portion between two adjacent equipotential lines and adjacent flow lines is called. The options are field or gap or potential drop or velocity drop. I'll repeat the question. Portion between two adjacent equipotential lines and adjacent flow lines is called. The options are field, gap, potential drop or velocity drop. Okay. Next question. The critical hydraulic gradient for a loose deposit of sand having specific gravity of 2.67 and void ratio of 0.67 is. I hope you know the concept of critical hydraulic gradient with respect to the quicksand condition. So for a loose deposit of sand which has specific gravity of 2.67 and void ratio of 0.67, what will be the critical hydraulic gradient? The options are 0, 1, 2 or 3. I'll repeat, the critical hydraulic gradient for a loose deposit of sand having specific gravity of 2.67 and void ratio of 0.67. The options are 0, 1, 2 or 3. The last question is, yes, the hydraulic head that would produce quick condition in a sand stratum of 2 meter thickness if G equal to 2.7 and E equal to 0.7 is. So the previous question, this is similar to the previous question except that here the critical hydraulic gradient The critical hydraulic gradient has not been asked. Instead, the hydraulic head has been asked, which will cause the quicksand condition. The options are same, 0, 1, 2 and 3. So I will repeat the question again. The hydraulic head that would produce quick condition in a sand stratum of 2 meter thickness if G equals to 2.7 and E equals to 0.7. So all you need to note down is the value of G, E, that is the void ratio, and the sand thickness, that is 2 meter. Okay, and then find out the hydraulic head. Okay, so it is 6:45 right now. Okay, I'm giving you 15 minutes time. You solve it. I'll again start the discussion at 7 o'clock. Okay, you can stay in the same meeting. I'll start at 7 o'clock. I'll start discussing the solutions with the explanation for the answers. Okay.
Yeah.
Am I audible? Hello, am I audible? Okay, so I will start with the solution part now. Yes. So the first question was, just a moment. The first question was factors affecting compaction of a soil are. What is the answer, anyone? Any answer? Factors affecting compaction of a soil are. Okay, so here we all know that moisture content, water content is an essential part parameter for compacting a soil. Soil type, yes, compaction of the soil depends on the type of soil being compacted, and definitely the compaction of the soil depends on the compaction energy. Depends on the compaction energy. That is the force with which the soil is being compacted. So here we can see that all the three, first, second, and third options are affecting compaction of the soil. So the answer is all of these. The answer is all of these. Okay. So factor affecting the compaction of the soil are water content, soil type, and compaction energy. So all of these is the answer. Okay. Next question. Okay. For the same soil type, the effect of heavier compaction is 2. What is the answer? Any answer? You can say the answer, or you can, type in the chat box if you have any answer. Which option or options are correct? Okay, no problem. So here we know that if we draw the graph between dry density and moisture content, here we have gamma D dry density and here we have W moisture content. So if this is the graph for a standard Proctor test, where this is the optimum moisture content and this is the maximum dry density, if we increase the compactive energy or compactive force, the graph will shift towards this, like this, where this will be the optimum moisture content and this will be the maximum dry density. So what's happening? Because of heavier compaction, the moisture content, optimum moisture content is decreasing. In the same soil, what is happening? Increase in the compactive energy, the optimum moisture content is decreasing. So first, this is the correct option, decrease the optimum water content, and the second point is what? There is an increase in the maximum dry density from this point to this point. So two answers are correct. Decrease the optimum moisture content and increase the maximum dry density. Okay, decrease the optimum moisture content and increase the maximum dry density. Okay, so both the options are correct, the first one and the fourth one. Clear? Any question, any doubt? Okay, next question. The water content used in field compaction is known as. This is a very simple question. Any answer? Anyone? Have you solved this question? Has anyone solved the questions? Okay. The water content used in field compaction is known as placement water content. Okay. It's just a terminology used for the moisture content used in field compaction. When we are compacting in the field, we use placement water content. Okay. Yes. Okay. Next question. The variables concerning the method used to compact a given soil include. Now, what are the variables that come into play? Someone gave an answer. A. Which question's answer is A? This one or the last one? I think you have told the last one, optimum water content. No, it is placement water content. Okay. And this one is a multiple select question. So more than one can be correct. Any answer for this? Okay, so manner of operation is very important while compaction. How the soil is being compacted, that is important. The weight of the equipment, that is the hammer which we are using to compact the soil, is important. Its weight is important, obviously. More the weight, more easily we can compact the soil in the less number of layers. Also, area of contact. Area of contact will define the number of blows we have to give, so that is also important. And time of compaction. If we compact the soil for more time, then it will be more compacted. Okay. So all these are the variables concerning the method used to compact a given soil. All these. Okay. Compaction depends on all these factors. Yes, time is an option, and also all the other factors. Okay, the manner of operation, how are we compacting the soil? By giving, vertical blows or inclined blows. What is the weight of the equipment which we are using to compact the soil? What is the area of contact between the equipment, the hammer used, and the soil mass? And for how long are we compacting the soil? These all are important. Okay. Okay. Next question. The line showing dry density as a function of water content in the absence of air void is called. What is the answer? The line showing dry density as a function of water content in the absence of air voids is called. What is the answer? If air void is absent, now dry density is a function of water content, that means moisture is present and air void is absent. That means the soil is saturated. The soil is saturated. If it's saturated, then the line is called saturation line. And another term also we can use, zero air voids line. zero air voids line, saturation line or zero air voids line. Okay, it is not called no air voids line, it is called zero air voids line or saturation line. Yes, zero air void line. Okay, so this is the answer. I'll go to the next question. In modified Proctor test, the soil is compacted in. Now this is an easy question. I think you can give the answer. How many layers of compaction in modified Proctor test? 5 layers. Yes, very good. 5 layers. In standard it is 3. In modified it is 5. So in modified Proctor test, the soil is compacted in 5 layers. Okay, good. Next question. A soil sample has specific gravity of 2.7 and optimum moisture content of 16%. What is the theoretical maximum dry density that can be achieved for this soil? What is the answer? Anyone has solved this question? Okay, see, the dry density is given in gram per cc. I'll write density over here. Dry density is given as, the formula is G rho W divided by 1 plus E. What is E? E is nothing but Wg by S. Wg divided by S. Okay, this is the formula from the index properties of soils. Now, for this to be maximum, for this part of the equation to be maximum, the S has to be maximum or this denominator has to be minimum. So if this is maximum, this is minimum. Okay, so this maximum value of S equals to 1. So I can write like this: rho D max equals to G rho W divided by 1 plus Wg. Now I'll just put the values of G as 2.7. Rho W is the density of water 1 gram per cc. W is the moisture content, that is 16, that is 0.16. So I'll just add 0.16 multiply with G 2.7, add it with 1 and then multiply G, that is 2.7 into divide by answer. I'm getting a value of 1.885. Okay, the answer is 1.885. Is it clear? So dry density is a ratio of the product of G and rho W divided by 1 plus Wg by S, or 1 plus E equal to Wg by S, that is moisture content into gravity, specific gravity divided by saturation. When rho D is maximum, S equals to 1. So the formula becomes G rho W divided by 1 plus Wg. Now this value of rho W equals to 1 gram per cc. Putting all the values, we get 1.885. Okay. Yes, 1.885. Good. Okay. Next question. A cohesive soil yields a maximum dry density of 1.8 at an OMC of 16%. Specific gravity is 2.65, void ratio, degree saturation, and MDD. Has anyone solved this question? Anyone? Have you solved this question? Okay, no problem. Just a moment. Yes. So here the void ratio. So the formula of dry density is what? Dry density gamma d rho d equals to G rho W divided by 1 plus E. From here we can get void ratio equals to G rho W divided by rho D minus 1. G rho W divided by rho D minus 1. This is the void ratio. Now put the value G equal to 2.65, rho D equals to 1.8, rho W equals to 1 gram per cc. So 2.65 divided by 1.8 minus 1. I am getting 0.4772. Just a moment. I am getting 0.4772. This is the void ratio. Okay. Any answer? Yes. Not 13. Not 13. Check it. It will be G rho W divided by rho D minus 1. G is 2.65, I believe. Yes, 2.65 divided by rho D, rho W by whatever written. Rho W by rho D I have written. Yes, 0 W by rho D. Rho D is 1.6, 1.8 minus 1, 0.4722. Please do it again and check it once. Now the degree of saturation. What is the value of degree of saturation? What is the formula? E equal to Wg by S. So S equals to Wg divided by E. So W is how much? W is 16% or 0.16. G is how much? 2.65. And E is, yes, S equals to, yes, 89.79%. Good. And E is 0.4722. You put the value of E 0.4722, W moisture content as 0.16 and G as 2.65. You will get 0.8979. In percentage it is 89.79%. 89.79 percentage. Okay, 89.79 percentage. Now the next one, maximum dry density. Okay, again for rho D to be maximum, what do we know in the formula? G rho W divided by 1 plus Wg by S. For this to be maximum, S equals to 1, isn't it? We cannot use the saturation degree which we obtained in part B. We cannot. Okay, we have to use dry density is 17.65. No. For maximum dry density, we have to use S equals to 1. Okay, it can be further compacted too. Now, currently with the dry density of 1.8, okay, with the dry density of 1.8 gram per cc, the moisture content, the degree of saturation is 89.79%. Now, how can we further compact the soil? To do that, we have to increase the moisture content so that the soil gets 100% saturated. Okay, 100% saturated. So we put the values of S equals to 1, W, same moisture content because the volume is different over here. G is 2.65. Okay, now see, we are compacting the soil in such a way that the optimum moisture content is remaining same. So what are we doing? We are not adding the soil. We are sorry, not the soil, the moisture. We are not adding the moisture or water. Okay, we are compacting it to reduce the voids so that more and more number of voids are filled with water only, or the air voids which was present. Okay, from there the air gets released and the voids gets closed. So here, since we are using the same moisture content, we are not adding water. Okay, we are not adding water, we are just releasing the air from the voids. The voids are getting either closed or shrinking so that it is only filled with water. All the voids are filled with water. Okay, that is the maximum density it can be compacted to where S equals to 1, W equals to OMC 0.16, G equal to 2.65 and OW equals to 1. So what is the answer? It is not 17.65. I believe the answer is close to 1.861, 1.86, something like that. You will do it and find it out. I'll just do it again. 0.16 into 2.65 plus 1 G 2.65 divided by answer 1.861. The answer is 1.861 gram per cc. Okay, 1.861 gram per cc. This is the answer. Okay, same formula which we have used in the last problem. Okay, I hope it is clear. I'll go to the next question. Seepage velocity is, what is seepage velocity? So there are two terms. One is seepage velocity, one is discharge velocity. Yes. Okay. Yeah. So in the case of seepage velocity, it is the actual velocity. Okay. Not considering the entire soil cross section. Okay. So it is the rate of discharge per unit cross section area of the voids. It is the actual, percolation of water. We don't consider the entire soil cross sectional area, though we consider the entire soil cross sectional area during solving the numericals and all those things, but in actually the soil is moving through the voids only. So that velocity, that rate of discharge is called seepage velocity. Okay, and the upper and the first option, there is the rate of discharge from cross sectional area of soil. This is called the discharge velocity. This is called discharge velocity. This is called discharge velocity. Okay. I hope it was clear. Go to the next question. Yes. A soil has a discharge velocity of 6 into 10 to the power minus 7 and the void ratio of 0.5. The seepage velocity in 10 to the power minus 7 meter per second is. Has anyone solved this question? Okay. So we know that seepage velocity is equals to the discharge velocity divided by n. N is the porosity. Okay, n is the porosity. So now to find out the porosity first. So we have void ratio given over here. So we'll find porosity from void ratio. Porosity equal to void ratio divided by 1 plus void ratio. I think that is the formula. Yes. Porosity equals to void ratio divided by 1 plus void ratio. Okay. So you solve this, you'll get a value of 0.5 divided by 1.5 or something like 0.33. 0.33. Now you put n equal to 0.33 and v, that is the discharge velocity, as 6, because 10 to the power minus 7 is constant in the question and the answer. So 6 divided by 0.33. 6 divided by 0.33. You get 18.18. So the second one is the correct option. The second one is the correct option. Okay. So this is very important formula. Seepage velocity equals to discharge velocity divided by porosity. Okay. Next question. Flow between any two points in a soil depends on the difference between. What is the answer? pressure head. Pressure head is one factor. Pressure head is just one factor. Okay, but when a soil is when water is flowing through a soil mass, then pressure head is what? Pressure head is the head created because of the pressure of water. Okay, velocity head is due to the velocity. There is the kinetic energy, and datum head is the head due to the elevation or the position above the datum or the sea level. So all three combined, initiates the flow of fluid between any 2 points in a soil mass or in a pipe, anywhere. Whenever water is flowing, so it is flowing because all these three factors combinedly, initiate the flow of water. Okay, so total head is the correct answer. So flow between any 2 points in a soil depends on the difference between total head. At point A, what is the total head? That is the summation of pressure head, velocity head and datum head. At point B, again summation of pressure head, velocity head and datum head. The difference between these two summation gives us the flow. Okay. Next question. Yes, falling head test. Anyone solve this question? What is the answer? Falling head test. Okay, so here we have to find out the value of K. The value of K is equals to 2.303 AL divided by AT log to the base 10 H1 divided by H2. Okay. Now small a, what is small a? It is the area of the standpipe. So the formula will be pi by 4 into d square. This is d. The area value we can obtain as 0.126 cm square. Or you can write pi by 4 pi by 4, cancel on the numerator and denominator, just write d square by d square, anything. Then again, what is capital A? It is the area of the cross section of soil sample. What is the diameter? 80 mm. Okay, 80 mm. This is d square and this diameter is d square. With a value of 50.265. 50.265 again centimeter square. What is L? This L, what is the L? L is the length, soil sample length. L, length. What is T? T is 6 minutes. T is 6 minutes. Convert this 6 minutes. T equals to 6 minutes, that is in seconds, that is 3600 seconds. Not 360, 360 seconds. Yes, 6 into 60, 360 seconds. And the area is in cm square, getting cancelled. L is in centimeter. It's okay. Now H1. H1 is the initial head. Initial head is 1200. This is H1. What is the final head? It is H2. That is 400. This is H2. Okay. Now put all the values and find out the answer. I believe it will be close to option B, 9.181. Yes, 9.181 into 10 to the power minus 5. 9.181 into 10 to the power minus 5. Okay. So formula is K equal to 2.303 AL by AT log to the base 10 H1 by H2. These are all the components. Small a is the area of cross section of the standpipe. Capital A is the area of cross section of the soil sample. L is the length of soil sample. T is the time taken. H1 is the initial head, H2 is the final head. So all these values put together, in the formula we get a value of 9.181 into 10 to the power minus 5. Okay. Next question. Permeability in certified soils. Certified deposits show greater magnitude in direction. Now, certified deposit means like this, it has layers. Now we know water can flow like this in this direction or in this direction. If it flows in this direction, we'll say it is KH, permeability in the horizontal direction, and vertically it is KV, the same in the vertical direction. Now for the horizontal direction, we have the formula KH equals to, if this thickness is Z1, Z2, Z3, and so on, and the K value is K1, K2, K3. Okay, K1, K2, K3. So we can write like this. KH is the arithmetic mean, weighted arithmetic mean, like K1 Z1 plus K2 Z2 plus dot up to Kn Zn divided by the total thickness Z1 plus Z2 plus up to N. Okay, this KH. Now KV is the harmonic mean. KV is the harmonic mean. We will write the total thickness in the numerator up to N divided by ratio of Z by K. Z1 by K1 plus Z2 divided by K2 plus up to N. So we all know this is the arithmetic mean, this is the harmonic mean. In general mathematics, arithmetic mean is always greater than harmonic mean. Okay. So KH will be more than KV. KH will be more than KV. Perpendicular. No, perpendicular is KV. Perpendicular is KV. Wait. Perpendicular certification, yes, it is KV. Okay. KH is parallel and KV is perpendicular. So KH is parallel. Okay. KH, this is parallel to certification, and this is the perpendicular one. So harmonic mean is less than the arithmetic mean, and harmonic mean is the perpendicular one or vertical or KV. Since arithmetic mean is more than the harmonic mean, so yes, so in this stratified soil deposits, the permeability will have a greater magnitude in a direction parallel to the stratification, that is KH. Okay, in this direction, basically, in this direction. I hope it was clear. It is simple because in parallel it is taking the arithmetic mean, but in perpendicular taking the harmonic mean. Arithmetic mean is always more than the harmonic mean. Okay. Next question. Yes, based on the previous formula, here we have, 3 soil layers. If you haven't solved this, please do it now. The first one is not given, so we'll assume the first one to be, K, the value of coefficient permeability, and Z, the thickness. Now it is said that thickness and permeability of the second layer are twice of the first. So for the second one, it is 2K and 2Z. Now, for the third layer, it is twice of the second. That means for the third layer, it is 4K and 4Z. This is 1, this is 2, this is 3. To find out the ratio of the average permeability in horizontal to that in the vertical direction. So you use the formula first. So KH equals to the arithmetic mean K1 Z1, K2 Z2, K3 Z3. It is KZ plus 4KZ plus 16KZ. So 16 plus 420, so it is giving us a value of 21 kz. The same formula which I have used previously in the previous one, 21 by control Z, yes. In the denominator it is what? Denominator it is the summation of Z. Summation of Z means how much? 4Z plus 2Z plus Z, it is 7Z. And numerator is kz, denominator is z, z get cancelled, it is k. It is k. Found out the answer? No. It is k. Now for the vertical one. For the vertical one, we have in the numerator is how much? It is the summation of all the z values. That is the total thickness. So 4 plus 2 6 plus 1 7z, again 7z, divided by the ratio of z by k. So z by k, again 2z by 2k, again z by k, 4z by 4k, again z by k. So z by k plus z by k plus z by k is 3z by k. 3z by k. So gets cancelled. We have k vertical as 7 by 3 k. Now the ratio between these two, kh is to kv. It will be how much? 21 by 7 into 3 by 7. It is divided by 7 by 3 means into 3 by 7. 7 3 is 21. The answer is 9 by 7. The answer is 9 by 7. Okay. So using the same formula I have used in the previous sum, that is kh equal to k1 z1, k2 z2, k3 z3 divided by z1 plus z2 plus z3. I have found out the permeability in the horizontal direction, and then again using the formula kv in the vertical direction, z1 plus z2 plus z3 divided by z1 by k1, z2 plus z2 by k2, z3 by k3. I have found out the permeability in the vertical direction, and the ratio of these two gives us a value of 9 by 7. Okay, I hope it was clear. I'll go to the next question. Calculate the coefficient of permeability in meter per day of a soil sample. Okay, so in this question, we have to first of all remember the basic Darcy's law, Q equals to KIA. And what is Q? Discharge per unit time. Discharge per unit time equals to K. I means the head divided by length into A. So what do we need to find out? The coefficient of permeability. Now, so rearranging the formula, K equals to how much? K equals to, we have Q into L divided by T H A divided by T H A. So over here A is 50. This is A. Okay. Time is in minutes. Time is in minutes. H, that is the height, is 6 centimeter. I believe, yes. 6 centimeter in height. So I think you have to convert this into, yes, 600. So this is the height, head of 40 centimeter. This is the H, this is head, and Q is 430 ml. This is Q. Now 430 mm is 430 cc. So we can see that the units are in centimeter, but time is in minutes. So for converting the time, just multiply whatever value you will get, 24 into 3600, and you will get, I think, the value of 600 centimeter means 6 centimeter means yes, the value of whatever you will get, to convert that into meter, divided by 100. So solve this, you get a value of I think 1.86. I'll just do it. 430 into L is 6 divided by 10 minutes into height, it is a head, there is a 40 into area 50 into 24 into 3600 divided by, okay, just a moment. Soil sample of 6 centimeter height. So L is 6, yes. Time, you can convert the time first of all into seconds, okay. Convert it into seconds, then only you can convert it into, day. Convert the time into seconds, so time will be 10 minutes, that is 600. Yes, time will be 600 seconds. 600 seconds to convert the whole thing into, first of all, centimeter per second. Then from centimeter per second you can convert the same to meter per day, because anyway centimeter per second is the easy and feasible unit to find out from this question, if it is either centimeter per second or meter per day. So first of all use t as 600, time into time as seconds, and then convert this whole thing into meter per day. Okay. Yes, it is 1.86. I hope it is clear. I go to the next question. The line within the dam section below which there is positive hydrostatic pressure. Yes. So if there is a dam section like this is the upstream side, this is the downstream side. This is the water level over here, this water level over here. So there is a line below which there is positive hydrostatic pressure and above which it is dry. This line is called the phreatic line. It's called the phreatic line. Okay. Next question. Soil at the toe of a dam has a void ratio of 0.62, G equal to 2.62. Factor of safety of 5, exit gradient. So first of all, to find out the exit gradient, we need to find out the critical hydraulic gradient, it is IC. IC. Yes, any question? Can we watch this lecture after the session? Yes, this lecture will be uploaded in YouTube. You can watch it after the session. I think you will get the link of all the sessions. Okay. So critical hydraulic gradient, that is IC, equals to G minus 1 divided by 1 plus E. G minus 1 divided by 1 plus E. So put the value of G 2.62 and E 0.62, you get a value of 1. You get a value of 1. Now factor of safety is how much? Factor of safety, it is the critical hydraulic gradient divided by the permissible exit gradient. I can write it as P, IP. So IP will be equals to how much? IP will be equals to IC divided by F. IC divided by F. So 1 divided by 5 with the factor of safety. The value is 0.2. The value is 0.2. So factor of safety, it is critical hydraulic gradient divided by the permissible exit gradient. From here we can find out the permissible exit gradient. Okay. Yes, 0.2, correct. Good. Next question. Elevation of a point with respect to any arbitrary datum is called. Any answer? This question has two answers. It is, since I'm talking about the datum and the elevation, it is called position head and also called elevation head. Position head and also called elevation head. Okay. So the summation of position head or elevation head and pressure head and velocity head gives a total head. Okay. No, total head pressure head is not the answer. I am talking about elevation of a point. Elevation from datum. Okay, pressure head is due to the water pressure. The pressure given by the water, that the energy it generates in terms of energy head, we call it as pressure head. Okay. With only with respect to the position, that is the elevation of a particular structure with respect to its mean sea level. It is called the elevation head or the position head. Okay. Next question. In a flow net. So yes, in this flow net sum, it is very easy. You know the quantity of seepage, that is the discharge. That is easy formula. Q equals to KH NF by ND. ND. Okay. What is K? K is given. What is H? Head loss 3. What is NF? Number of flow paths. That is 4. What is ND? Number of equipotential drops. That is 15. So what is the answer? So solve it. 4 by 15 into 3. Is 1.6. 1.6 into 10 to the power 5. Okay. So Q equals to KH into NF by ND. This is the formula for finding out the quantity of seepage. Seepage pressure is, it is a very easy question, basic conceptual question. It is the pressure exerted by percolating water on the soil. Okay. In any direction, it can be horizontal or vertical, down or vertical up. But any pressure by the percolating water on the soil is called seepage pressure. Okay. Next question. Again the same, discharge meter cube per second. Now again the same formula, Q equals to KH into NF by ND. NF by ND. Now in this case there is a dam. Okay. 52 meter height with 2 meter freeboard. Freeboard is the distance from the water level to the top of the dam. This is 2 meter. What is the head loss? This is the head loss, H. So if the height is 52, what is H? This minus this, 52 minus 2, that is 50 meter. So H is 50 meter. What is NF? Flow channel, that is 4. What is ND? ND is number of drops, that is 25. So solve it. 4 by 25 into 50, that is 8 into 3 divided by 1000. I'll believe 10 to the power minus 3. No, 4 by 25, and it is 25, yes 50, 3 10 to the power minus. Okay, the discharge is in, the discharge is in centimeter per second, okay, and we want the discharge in meter cube per meter length. So you have to convert this because you are using H in meter. Okay, so K will also be in meter per second. Okay, K will also be in meter per second. So convert this centimeter to meter. So 3 into 10 to the power minus 3, it will change to 3 into 10 to the power minus 5. 10 to the power minus 5. Okay. into 2 into 4. So it will be 2.4 10 to the power minus 4. That is, I believe, the second option. Have you solved it? Okay. So the value of K is given in centimeter. All you have to do is change the value into meter. We get meter square per meter cube per meter. Okay, that is meter square only, but we'll write as meter cube per meter. So change this unit into meter. So it will be K, the value of K will be 3 into 10 to the power minus 5 meter per second. Okay, meter per second. Then we get the value of 0.00024. Okay, 0.00024. Okay, next question. The point between two adjacent equipotential drops, equipotential lines and adjacent flow lines is called. Okay, so if this represents a drop in the head during the flow, and this line represents the stream lines or the flow lines, the portion between two adjacent flow lines, between this and two adjacent equipotential lines, sorry, the portion between two adjacent equipotential lines between this and two adjacent flow lines, that is between the upper one and the lower one. So this is the position. What is it called? It is called field. Okay, it is called field. The portion between two adjacent equipotential line and two adjacent flow lines is called a field. Okay, next question. Okay, this is easy. The critical hydraulic gradient, IC, the formula is G minus 1 divided by 1 plus E. So G is 2.67, 2.67 minus 1 is 1.67, and E is 0.67, 1 plus 0.67 is 1.67. The value of I becomes 1. Okay, so this is the formula you have to remember for solving these questions. Very important. IC equals to G minus 1 by 1 plus E. Now in the next question, the same question with a bit of twist. See, I have asked to solve the hydraulic head. Solve the hydraulic head. So again here we have G and E. So hydraulic head, that would produce quick condition. So when quick condition is produced in a sand, that means it has reached the critical hydraulic gradient. On the verge of critical hydraulic gradient, if it goes beyond that, then quicksand condition will be produced. So we have to first of all find out the critical hydraulic gradient. IC equals to G minus 1 by 1 plus E. Again here I have given easy values. 2.7 minus 1 is 1.7, divided by 1 plus 0.7 is 1.7. So value is 1. The value is 1. Now I see this is the head, right? IC equals to the hydraulic head divided by the path of travel, of the water. Okay. Now the path of travel is equal to the thickness. What is the thickness? Thickness is 2 meter. So from this we can find out the hydraulic head H equals to IC into L. Critical hydraulic gradient into the thickness of the stratum. So 2 into 1, that is 2. Hydraulic head is 2. Okay. And the unit is 2 in terms of meter. 2 meter. Okay. Okay, I'll just recap the ones I've shown. Yes, after this was the sum Q equals to KH NF by ND. Then this was the seepage pressure. This was the again the same discharge Q equals to KH NF by ND. Yes, this was the portion between the equipotential lines and the adjacent flow lines called field. This was the sum of the critical hydraulic gradient, that is I is equal to G minus 1 by 1 plus E, and this is the again hydraulic gradient that will give us the hydraulic head. Okay, so I hope the session was understandable. Thank you for attending the session. We'll meet again in the next, session on coming Monday. On coming Monday, in the next session, we'll meet. Okay. Thank you so much.